Now, we've done independent segregation for 2 genes, but you can expand it to 3, 4, 5, however many you want. Okay, so one thing you can imagine then, for example, is a mom who, instead of 3 independent genes that are on 3 different chromosomes, she's big A, big B, big C, and then the sperm coming from dad, okay, little a, little b, and little c, okay, produces a diploid individual, okay. And what I'm going to do is I'm going to show the diploid individual after S phase, after 1 round of replication, just prior to entry into meiosis. Okay, so the chromosome arms of the chromatids, this. But what we're going to imagine instead is they segregate in a particular way like this. Okay, excuse me about that. Alright, they segregate like this, or they set themselves up for segregation like this. Okay, so big A, big A, big B, big B, big C, and then conversely over here, little a, little b, little b, and then over here, little c, little c. Okay, now if you think about it for a second, there's a bunch of different ways in which these can be arranged, okay? So, any particular way is, this could be this way, or this could be that way, or this could be that way, and regarding that, you can just multiply out the probabilities for any particular way that they're arranged, okay? So, the probability that these are this way is just the way they are, and then the probability then that B is on the same side as A, okay? Excuse me, big B is on the same side as big A would be a half, okay? And the probability then that big C is on the same side of big B, if that had happened, is also equal to half. So there's, if you think about it, there's essentially 4 different ways, or 1 out of 4 different ways. You might think it's 1/8, but it's not, because these can be arbitrarily arranged. The question is whether they line up together, parental with parental, mom with mom, for each of the sets, okay? So, let's calculate the probabilities of these types of arrangements. Well, if this type of thing actually were to occur, then you would definitely get either, okay, because these all segregate this way, gametes like this, okay, big A and then big C together with little b in here, okay, or you would get the other corresponding gamete, okay, which is equal to, which would be little a, oops, big B, and little c. Okay, so that arrangement can happen in this particular way. There's 4 different ways that these can be arranged, and then there's a chance of this and a chance of this. So 1/4 times 1/2 for getting this particular arrangement. The probability of this arrangement, okay, up here is equal to 1/4, okay, and then the probability of either one of these, okay, is 1/2, okay, so probability 1/2, conditional on this particular arrangement, probability of the gamete coming this way, conditional on this particular arrangement. So the probability that you get in the total sum of this particular gamete is equal to 1/4, so this, make that an arrow, is equal to 1/4 times 1/2, so 1/8 of the time you'll get this particular gamete. Okay. Now, another way of thinking about this, without doing all the gymnastics of a bunch of meiotic products, is just to consider these probabilities of independent segregation. Okay, so you might be given a problem. We already did a problem like this. We have an individual that is this particular genotype. Okay, big A over little a, big B over little b, big C over little c, and then big D over little d, okay? And you cross this individual with maybe sort of a test cross type situation. You're not sure exactly what this genotype is, but anyway, this individual is little a, little b, little c, and then little d, little d. Okay. So what you might want to do is then calculate, if you cross this individual, what's the probability that any particular progeny has any particular genotype. Okay, well, this is guaranteed to transmit only little a, little b, little c, little d gametes, and so you can kind of just draw this at the bottom for the known gametes that come from this individual down here, little a, little b, little c, little d. Okay, so then you can think of how does Mendel segregate these ones? How does meiosis segregate each of these? Well, it's a probability of a half. Okay, so there'd be a probability of a half that this individual got big A. Okay, and then there'd be a probability of a half that this individual also inherited big B. And there's a probability of a half that this individual inherited big C, and there's a probability of a half that this individual inherits big D. Okay, so 1 out of 2, 1 out of 4, 1 out of 8, 1 out of 16. The probability of this particular genotype in this particular case is probability is equal to 1 out of 16. Okay. Now, of course, you can even elaborate that even more and imagine more complex types of genotypes. For example, what if this individual was big B, big C? Okay. Well, you can kind of think about it as just sort of like, well, the only way that this can occur, for example, well, what's the probability of getting now, for example, an individual that's little a, little b, little c, excuse me, little b, little c, and little d, okay? Well, what has to happen? Well, it has to segregate. In meiosis, this individual has to transmit a little a, little b, little c, little d gamete, okay? And what is the probability of that? 1 out of 2, 1 out of 4, 1 out of 8, 1 out of 16. So the probability is 1 out of 16, which is the 1 out of 16 that you get that scenario coming from this individual. And so that's a typo there. And then what's the probability of little a, little b, little c, little d coming from this individual? Okay, that has to mean that this individual transmitted this particular gamete. Okay, well, this is guaranteed. Okay, there's a half chance of that. Okay, so probability of a half for here. Likewise, a probability of a half for here. Okay, and then it's guaranteed to always transmit little d. So probability that this individual transmits a little a, little b, little c, little d gamete is 1/2 times a half, so it's 1/4. Okay, so the total probability that you get this individual is equal to the probability of this individual transmitting the gamete is 1/4. Okay, that's this. Okay, times this 1/16. Okay, so 1/4 times 1/16. All right, and so that's a way that you can sort of, again, think about independent segregation happening in meiosis. And here we're not drawing the whole rigmarole in meiosis, but you can get an idea of how meiosis and independent segregation are very tightly intercoupled with one another.